Yeah, so we will do a slide switch, but welcome to the session on statistical inference. And the first talk will be held now by Yuwen Cheng from North Carolina State University on the topic of inference for optimal linear treatment regimes and personalized decision making.
Welcome to my presentation, the inference for optimal linear treatment regimes in personalized decision making. And unfortunately, due to the visa constraints, I cannot be there with you in Barcelona. I'm thankful for the chance to present our paper virtually. This project was conducted in collaboration with my advisor, Dr. Shu Yang. So to give you an overview of the project, I will proceed in the following orders. First, I will introduce the concept of the individualized treatment regimes, the ITRs. Then I will discuss the methods of inference for the linear estimated ITRs, both from theoretical and practical perspectives. Following that, I will present one simulation and one real data application. Finally, I will conclude the presentation with a summary. So first, let's start from the background. The personalized decision-making is popular these days, is customized decisions based on each individual unique and own characteristics. So this approach is used in many areas. For example, the personalized medicine, which tailors the medical treatment to suit individual patient characteristics, ensuring that each patient can receive the most effective treatment. This is very important because the effectiveness of one treatment can vary significantly from one person to another. What works well for one person might be ineffective for another. Another key application is the personalized recommendations. So this enhances the user satisfaction and engagement by delivering the content and the products that are closely aligned with individual needs. So we understand the importance of the personalized decision making. Let's explore how it is applied. So our focus will be on the personalized medicine actually, and the concepts are similar across other applications. So the approach is to learn the individualized treatment regime, the ITR, which is a function mapping from patient information to a recommended treatment. So the big goal here is to find the optimal ITR, where the optimal ITR can maximize the mean outcome in the entire population. The mean outcome in the entire population given one ITR is called the value function. So when it comes to the individualized treatment regimes, the ones that are transparent and easy to understand are our top choices. Therefore, we focus on the interpretable ITRs. So they are important because the black box models are tough to trust due to their complicated and not transparent. Just like a magic trick, you cannot figure out what is happening behind the curtain. So the patients and the doctors feel more at ease with treatments when they know the reasons behind the choices made. So for the interpretable individualized treatment regimes, there are several types. The first popular one is the linear regime. So the linear regime is easy to understand and communicate. Each variable in the linear regime is given a coefficient that can indicate its influence. The magnitude and the sign, the positive sign or the negative sign of the coefficient can reveal the variable's importance and the variable's type of impact. So for our project, we focus on the linear regime here. Another popular interpretable ITR is the decision list, which is a sequence of the if-then statements. So below, we present one simple example of the decision list. So after introducing the background, let's discuss our methods. First, let's set up the statistical framework. Denote XAY are the observed data, and X is the L dimension covariates. A is the treatment, and Y is our outcome. YA is the potential outcome if the treatment was received, if the patient is received treatment A, and D is the individualized treatment regime, the ITR. YD is the potential outcome under the ITRD. VD is the value function under the ITRD, and we focus on the linear treatment regimes. One important thing to notice is that in the linear regimes, the value of the beta is not unique and can vary by scale. Therefore, here we only focus on the beta values that has been standardized to the unit length. Our goal is to find out this optimal linear regime, which can maximize the value function and under the given linear class. We focus on the linear regime because they are straightforward, easy to explain, easy to understand, and the magnitude and sign of the coefficient can reveal the variable's importance and the type of the impact. So how can we estimate the linear ITR and conduct inference on it? So let me first give a big picture here. So the linear ITR is designed to maximize this value function. First, we need to estimate the value function. We estimate the value function based on the AIPW estimator, and then we can derive the estimated linear ITR. Then we develop the asymptotic distribution of the estimated linear ITR and apply the bootstrap methods for inference of the estimated linear ITR in real-world applications. So not all of the potential outcomes are observable. Therefore, the value function is not identifiable. Here we present three fundamental assumptions in the causal inference framework. So the first assumption is the suitable assumption, which tells us that the outcome we see is the same as the potential outcomes when the corresponding treatment is given. That means when individuals' potential outcomes do not change based on the treatments other people receive and other people's potential outcomes. The second one is the treatment ignorability assumption, tells us there's no aberrant confounders based on all of the observed queries X. The treatment is independent with the potential outcomes. The third one tells us that the point score is always larger than 0. So here we denote EX as the point score and mu AX as the outcome mean function. And based on the previous three assumptions, we can write the identification formula for the value function. Here, rho is a function based on the point score and the treatment, and mu d is a function based on the outcome mean function and the ITRD. So based on this identification formula, Zhang et al. In 2012 introduced this AIPW estimator, where rho hat and mu hat d are derived by substituting the estimated point score and the estimated outcome mean function into rho and mu d respectively. So the beta 0 is the true linear ITR, which maximizes the true value function. Beta hat is our target, is the estimated linear ITR, which maximizes the AIPW estimator. One nice property of the AIPW estimator is that it is doubly robust, which means if either the point score model or the outcome mean model is correctly specified, then the estimated value function is consistent for the true value function. However, even with this nice property, choosing the right parametric models for real-world data can still be a challenge. That's why we often turn to the flexible non-parametric or semi-parametric models. These models can always converge to the true functions, but they have another trade-off. They converge more slowly. Here, let's first study the AIPW estimator. We derived a symptotic distribution of the AIPW estimator. So to derive the theorem, we need to satisfy this assumption, which tells us the product of the estimated point score and the estimated outcome mean function should converge to their true forms in the root NL2 convergence rate. So this rate can be achieved if each component will converge to their true forms at the n to the negative 1/4 power rate. And a variety of semi-parametric models can satisfy the n to the negative 1/4 power rate, such as the GAN model, the single index model, and so on. So based on this assumption and also other assumptions listed in the paper, we can have this theorem. First, the beta hat can converge to the true value beta 0 at a cube root rate. And then the AIPW estimator is asymptotically normal. So this normality is good, but the question arrives based on the cube root rate. This cube root rate makes it difficult to analyze the beta hat itself, both in theory and in practice. And we will solve them one by one. So here we start to study the theorem of the estimated linear ITR. To derive the cube root asymptotic distribution of the beta hat, one important assumption is that both the estimated point score and estimated outcome mean function should uniformly converge to their true forms at a rate little o of n to the negative 1/3. So this rate is quicker than what we have discussed before, and uniform convergence is also more strict than the L2 convergence. To achieve this convergence rate, we first assume that point score and outcome mean function are in the Holder class with the smoothness order S larger than L, where L is the dimension of the covariates. Then the optimal uniform convergence rate that one estimator can achieve will be the little o of n to the negative 1/3. So there are many estimators to achieve this optimal uniform rate, such as the series estimators and the local polynomial estimators. Based on this assumption and also other assumptions, it's in the paper, we can derive the asymptotic distribution of the beta hat. So beta hat converges to the distribution that can maximize the non-zero Gaussian process WT plus a quadratic form here. So the H matrix is the negative second derivative of the value function given beta equals to beta 0, and we assume H is positively definite, and this positively definite assumption is one of our assumptions. So even we study the asymptotic distribution of the beta hat, we cannot apply it in real applications because it is too complex. Therefore, we need to utilize the bootstrap for inference. However, the cube root rate makes the traditional bootstrap fails. Here, we briefly introduce why. So for this one, it can be divided into two parts, where the first part can converge to the zero mean Gaussian process. The second part can converge to the quadratic form. Similarly, in case of the traditional bootstrap, where beta hat star represents the bootstrap version of the estimated linear ITR, we can also divide this formula into two parts. The first part can still convert to the zero mean Gaussian process, but the second part cannot convert to the quadratic form, which makes the traditional bootstrap fields in cube root asymptotic distributions. To address this, here we applied method developed by Daniel in 2020 for their updated bootstrap approach. So what they did is that they modified the original beta hat into this V tilde and used this V tilde to determine the bootstrap version of beta hat by maximizing the sample mean of the V tilde. Here, Hn is an estimator of the previous H matrix. This is algorithm about how to derive the bootstrap version beta hat. First, based on the original data, we compute the beta hat. And then based on the beta hat and the original data, we compute the Hn matrix. So there are two important things to notice is that we only compute Hn matrix once. Secondly, for the Hn matrix, there is one tuning parameter epsilon n here. In the third step, based on the beta hat and Hn matrix and the bootstrap samples, we can compute the beta hat star. And we can repeat the third step multiple times to generate multiple draws for the bootstrap. From here, we derive one finite sample simulation to evaluate the bootstrap method for inference on the estimated linear ITR. So this is how we generate our data, and to achieve the required uniform convergence rate, we apply the GAN model with the cubic smoothing spline for each univariate covariate to estimate the point score and outcome mean function. So in our data generation process, the optimal treatment regime is actually one linear regime. And because we focus on the beta values that has been standardized to the unit length, the true beta 0 values are as follows. Beta 01 equals to 0.894, 0.02 equals 0.447. So as we mentioned before, in the HN matrix, there is one tuning parameter epsilon. If we want to identify the optimal tuning parameter epsilon, which can minimize the approximate MSE, the optimal epsilon value actually requires the estimated H matrix and estimated Gaussian process kernel, queries kernel, which is a challenge and even unachievable in reality. Therefore, we evaluate multiple epsilon values to identify the most suitable one. So this table represents the estimates for beta 01, beta 02, denoted as EST, and their 95% quantile confidence interval coverage rate, denoted as coverage, and confidence interval length, denoted as length. And this table tells us that in our simulation, the optimal epsilon values is about 0.5 because it achieves a 95% coverage rate and the shortest confidence interval length. So here we present one real data application. We use the EICU CRD data, which is a multi-center repository of the anonymized healthcare records spanning across the United States from 2014 to 2015. And it consists of the patients who suffer from the sepsis. So we include 10 covariates acts, including the age, BMI, temperature, mean blood pressure, and so on. So our outcome is the negative absolute value of the cumulative flat balance, because the extreme values of the cumulative flat balance could be a problem. The larger one is, the better one is. Our treatment is whether to use the vasopressor versus others. So as we mentioned in the simulations, selecting the optimal epsilon values can be a challenge for the bootstrap method. For practical applications, we recommend choosing the epsilon values that correspond to the local minimum values in the confidence interval length. So actually that strategy guided our choices of the epsilon values equals to 0.05 for the simulations, where the 0.05 value yielded the shortest confidence interval length and the coverage rate close to 95%. Similarly, here, first we conduct sensitivity analysis across various epsilon values, and then we identify 0.3 and 0.5 are the local minimum values for the local minimum in confidence interval length for most variables tested. Therefore, we choose epsilon values equals to 0.3 and 0.5. So based on these two epsilon values, we have two findings. The first finding is the temperature. It has a positive effect. That makes sense because sepsis usually causes fever. The next finding is the red blood cell count, the WBC count, which also has a positive effect. And this is also consistent with the medical literature because sepsis always coincides with the high white blood cell counts. Finally, we summarize our presentation. We present asymptotic distribution of the AIPW estimator, and we explore the non-normal asymptotic distribution of the estimated linear ITR with the cube root convergence rate. And we apply the Daniel et al. method in 2020 to infer the cube root distribution for the estimated linear ITR. And there are some future directions. First, we can apply our method to the multi-stage treatment regimes with a variety of treatment choices at each stage. And what we focus on now is the continuous outcome. And this can also be generalized to the multiple other types of outcomes, such as binary outcome, count outcome, and survival outcome. And we focus on the inference on the estimated linear ITR, but it is also an interesting topic for another popular interpretable ITR, the decision list. Thank you for listening. Do you have any questions?
Thank you very much, Yuwen, for the very nice talk and also staying perfectly in time. I'm very impressed. Are there any questions? So maybe we start at the back.
Thanks for the great talk. So you were doing the estimation part non-parametrically. You were mentioning series estimators and splines. But what I'm wondering is, assuming a linear optimal treatment regime, does it have any implications on the outcome mean model or the propensity model? Does this assumption impose any restrictions on this? Thanks.
Do you mean, can you repeat again what assumption you mentioned? Do you mention this assumption, convergence rate?
So my question is, if you assume that the optimal treatment regime is linear in the covariates, would it imply anything? Would it have any implications on the outcome model or the propensity model? Or, yeah, that's it.
So you mean if it is if it is failed to assume the linear treatment regimes, is there any opinions for the outcome mean model and propensity score model?
Yes. Yes. So I'm asking this because I'm wondering, well, if we are willing to assume that the optimal regime is linear in covariates, would this also allow us to impose more structure on the outcome mean model or the propensity model to make the estimation easier?
I would say it is. Yeah. I would say first it is subject. It is it is subject based on each people's own opinion, and it is from my perspective. It is something similar to the variable selection. So if we can select the important variables based on the linear treatment regimes, I would say if it can make it easier for the outcome mean model and propensity score if only using the selected variables.
Thank you very much.
Okay.
So I think Robin. Oh, okay. So yeah, one question I wanted to ask is, so one thing I noticed is this reintroduction of parametric models with the argument of interpretability. So I wanted to ask, did you investigate what is the loss in performance you get for imposing these parametric assumptions? Or do you expect that there be a loss? Is there like a interpretability performance trade-off?
You mean if we apply the semi-parametric or non-parametric models, is there any loss for the inference?
No, the linearity assumption on the treatment regimes to which you restrict yourself?
Yeah, there should be some loss because first you assume that the treatment regime is actually one linear one. So but there is one trade-off because it is more easy to explain and more easy to inference because right now there are two ways for the interpretable ITRs. One is the linear regime, the other is a decision list. But for the decision list, the inference is much more complicated and even more harder to achieve. So there is a trade-off. You can easier to do that, but you also lose some information because you assume it is linear. It is a linear regime.
Okay, thank you very much. I think we can move on to the next speaker. So the next